Machine learning to train an artificial neural network. It's the modern way to make an AI. Now, as I've said, technically we've never made an AI. We will eventually, but we haven't yet. Because to me, AI implies an actual life form, an artificial life form. But I'm just being pedantic because AI, the term, is commonly used to refer to any computer program that is or is pretending to be an artificial life form. It even is used in video games when you have a player that's controlled by the computer, a character that's controlled by the computer. It's often called an AI character. So, AI it is. Now, you can make what's considered an AI without a neural network. That's very common, such as in video games. Look at Mario Party on the Nintendo 64. They definitely are not using a neural network there. But the thing about neural networks is we have developed powerful training techniques to allow us to have the computer program essentially write itself. So, traditionally, you would have a very smart programmer or several very smart programmers who would work for hours and hours and hours and hours manually creating a good AI to control a video game character or something of the sort. But the benefit of training a neural network is that it can be done offline. For example, you have the smart programmer set up the training session, but then you leave it overnight or for a month or two. Sort of like setting up your cooking in the kitchen and then going and doing something else while it's simmering. Having the computer program write itself is really a good way to look at what's going on. In fact, trying to figure out how neural networks actually learn is an active field of study. We've discovered several things. For example, when I get into convolutional neural networks in the future, I'll explain some of the things that they have found out about how those learn, but for the most part, neural networks are a black box and we're still trying to discover just why all of this works. The same way we're trying to discover all of the bits of the brain. We understand parts of the brain do things by checking MRIs and such, and seeing activation patterns, and we can get some clues, but we don't understand at the neural level, at the neuron level, what's going on. The same for computers. So there are three major types of machine learning: supervised, unsupervised, and reinforcement. There's also semi-supervised, which is just a blend of supervised and unsupervised, so that's not really a separate kind. It's just half and half. And then there's meta-learning. It's not really a separate category, it's just an application. So supervised, unsupervised, and reinforcement. So supervised learning is sort of like if you have a student who is trying to learn and they have a tutor. They have a textbook, a tutor, whatever. And at the beginning of training, at the beginning of learning, they have tools they're learning with, such as the textbook, and they have a specific goal in mind. That's the key to supervised learning. There is already a goal in mind. You already know completely what you want the neural network to do at the end of training. You already have a plan, you already have everything laid out, you just need to train the neural network to do it. That's supervised learning. So you have a data set that you want the neural network to work on, such as pictures. All pictures that ever have existed, do exist, and will exist. And then you have a training set, which is known pictures. For example, let's say you want to train a neural network to tell you whether or not there is a cat in a picture. Your training set is pictures. Some of them have cats, some of them don't, and they're labeled. Everything is labeled. You'll see that term, labeled. The pictures are labeled cat yes or cat no, and that's your training set. But then you have all these pictures that are unlabeled, and you can't even say, well, if we had all the people in the world working, we could label all the pictures. People will take new pictures. The idea is you want to create a neural network, an AI, that until the end of time will tell you whether any picture that someone happens to take has a cat in it. So that's the key to supervised learning. You have a training set, and you have to train the neural network with a set to make it do a task for pictures it's never seen before. Now, one of the big issues with supervised learning is something called overfitting. Basically, the way you train the network is you show it a picture of the cat, and you ask the network, is this a cat? And if the network's wrong, you tell it it's wrong. And then that's part of the training, is it makes itself a little less wrong. So you keep showing pictures and pictures and pictures, and you ask it what it thinks the answer is, you tell it what the answer is, you use something called backpropagation usually. We'll worry about the math later, but basically, it gives you the answer it thinks it's right, you tell it what is right, because you already know, supervised learning, you already know the answer, and then it corrects itself over and over and over, and over time, it starts identifying all the pictures correctly. But if you train it too much, if you just take a network and train it over and over and over for months on this training set, it will become absolutely perfect at identifying that training set. But if you show it a picture it's never seen before, it's going to give you an off-the-wall answer that means nothing, because it has essentially memorized the training set perfectly. It does not quote-unquote understand what a cat is. It understands, well, I mean, just like a human, it has memorized the answers for this training set without understanding, so to speak, what a cat is, so it can't identify anything except something in the training set. This is called overfitting, where if you have data points, right? Have you ever seen a plot? You have a bunch of data points and somebody draws a line through it. I believe they called it regression analysis, to basically say, well, these points are kind of scattered, but that's error, so you just draw a line through and that's the actual trend. That is what we want the neural network to do. We want the neural network to identify that line through the points that represents the general trend of the lines. Whereas if you train the neural network too much, it's just going to connect the dots, and it's going to draw from a dot to dot to dot, and it'll be this weird squiggly line that doesn't mean anything. So there are techniques to prevent overfitting or combat overfitting that, once again, I'll get to when I actually show you a real functional neural network training system. I just wanted to explain the basic for you right now. And it correlates exactly to a human. Think about it in terms of human learning. We're modeling a human neural network for a reason. You can think of a student in a class memorizing the answers to homework or off of a lecture board or whatever and not understanding, versus a student who actually understands and can solve future problems. That's what overfitting is. So supervised learning is just, you have a task and you train it to do a task, and that's it. The simplest form. Unsupervised learning is actually the trickiest and, in some ways, most interesting. Not the one I'm most interested in, but perhaps the most involved kind of neural network training, in my opinion. But anyway, in this case, unsupervised learning is like you have that student and they have their data. You have a student, you give them data, but there's no tutor, there's no textbook, there's no labels, it's just data. And these data are unlabeled. An example I've seen on the internet is, let's say that you have never seen a game of sports. You've never watched a TV match, you've never been to one, you know that sports exist, you know that balls get thrown around or whatever, but you've never seen a sports match. And then somebody sits you down in front of a TV and makes you watch one. And you've got a pitch or a field or whatever, people running around it, there's balls being thrown, they're wearing uniforms, they're doing all these things, and you have no idea what's going on. So your brain, and humans are very good at this pattern recognition, your brain is trying to figure out what's going on, so you start looking for similarities and differences. You'll notice that some of the people are wearing a green outfit and some of the people are wearing a white outfit, and they tend to cluster together most of the time and sometimes cross over. You'll notice that they have certain equipment. You'll notice patterns in how they move. You'll start to notice formations. You'll notice how the crowd reacts when the ball goes in the net versus when it doesn't go in the net. When somebody falls to the ground, there's all these things you notice, and you figure out, without any prompting, without knowing anything besides there's a score and one side wins. You don't know anything about sports, but you will figure out the concept of there's two teams and they're competing, and certain people have certain roles, and you will actually learn some of the rules of the game partially correctly or even fully correctly, if you have enough data, just from watching, having never seen it before. That is unsupervised learning. You have data, and the neural network is trained to figure out the underlying order that the human has not provided. There are two main types of unsupervised learning: clustering and dimensionality reduction. Clustering is the concept of trying to figure out things that are related to each other. Like if you have a population, you just have a picture of a crowd. Let's say it's just a crowd in a busy town square. Just a bunch of people. That's just noise. You know nothing about these people. There's nothing labeled. It's just a picture of people. But if you look at it, you start seeing those similarities and differences. You may notice people have long hair or short hair, or people are wearing dresses versus shorts. You may start identifying these look male or female. And it's not going to be a perfect division because there are females with short hair, there are males who wear dresses, but there is clustering. Maybe you are looking at a parking lot. Maybe you have a picture of a parking lot, and you'll start to identify these vehicles have 4 wheels, these vehicles have 2 wheels. These are overly simplistic examples, obviously, but this is what clustering is. The neural network learns to find groups that are very similar to each other. When you have that crowd of people, when you have that crowded parking lot, there's obviously a whole slew of differences. You have four-wheeled sedans that come in every color, and you have motorcycles that come in every color. But the sedans and motorcycles have something in common. If you have a blue sedan and a red sedan, and a blue motorcycle and a red motorcycle, the two sedans and motorcycles are more in common with each other because they have more traits, their size, their wheel count, number of seats inside, whatever. There's a lot of things about them that are similar, whereas if you compare a sedan, a red sedan, and a red motorcycle, they're both red. So there's less similarity there. So the neural network will cluster the most similar things. And if it's mostly red sedans with a couple blue sedans, those blue sedans will be a little further from the cluster of red sedans, but they'll be a lot further from any motorcycle. Very little in the universe is truly random. There will be similarities, there will be clusters, and this technique finds them, and then the human can look at what the neural network found and figure out why it found it to analyze a big group of data. The other thing is dimensionality reduction. You've got feature selection and feature extraction. A feature is just a property, it's an adjective. I have a height, I have a weight, I have a gender, I have a sex, I have a hair color, I have all these properties. I also have a personality. I have an attitude. I have a current state of wakefulness. I have a value to society. Anything that you can use to describe someone, that you can say this person has this property in this amount, is a feature. And that feature can be labeled in supervised learning or unlabeled in unsupervised learning. Feature extraction is similar to clustering, except instead of trying to find groups of data that are similar, data points that are similar, you're trying to figure out what about those points is significant. Basically, what features differentiate the data points more than other features, making those points more important. Let's say you have your parking lot again, and you've got four-wheeled vehicles and two-wheeled vehicles, and all the vehicles come in every color. Every color is a four-wheeler, every color a two-wheeler. So color doesn't really differentiate too much. It doesn't matter what other properties the vehicles have. You're going to find those properties associated with all these different colors. But the number of wheels separates, and you could cluster based on number of wheels, for example. So number of wheels is going to pop out as an important feature in feature extraction, whereas color won't. Feature extraction is kind of like a precursor to clustering. Feature extraction tells you, or the neural network that learns feature extraction tells you, how properties could be used to usefully cluster these objects. That was feature selection. If I said extraction, I meant selection. Feature extraction is, again, related. All of this is related, but it's kind of like compression. So instead of just trying to identify the most useful features for clustering, you remove the features that are not, and you use the remaining features to represent the data. Imagine that you're trying to describe a dog. You have to do it verbally. You can't just show a picture or whatever. How would you describe a dog? Well, you might describe it as a certain height, and it's got floppy ears, and the ears are brown, and it's got a black nose, and it's got a long snoot. You know, you can go pretty detailed, or you can go rough. You could say, oh, it's a small four-legged animal that barks. So you've described the dog, or you can describe it in great detail. And the level of detail is how many features you have decided to remove and not need to describe to still usefully describe the animal. For example, if you describe a dog as brown, you could describe a dog as brown, but its nose is black, and it's got a tiny little white patch on its shoulder, and the inside of its ears are pink, and its tongue is pink, and its eyes are white, or the whites of the eyes, rather. You know, the dog is not a universal brown. But if we say a brown dog, if somebody says to you, I have a brown dog, my dog is brown, you immediately know what they mean. And so you have simplified the description of the dog. It takes less information, less space to describe that dog than everything. And this works with populations as well. You may have seen images compressed, and you have the full quality image, and then the more you compress it to take up a smaller file size, the crappier it looks. But you can still tell what it is to a certain extent if you don't go down too much. If you have a crappy, grainy JPEG artifacted picture of a dog, as long as it's not 3 pixels big, you can still see it's a dog. You've lost information, but you can still see, oh, it's a brown dog, and it's sitting down, and it's on grass, or something that looks like grass. Same thing. You can compress a huge data set. Let's say you are modeling an animal population, you give them GPS and you take pictures and all this other stuff, and you get this huge data set of every little thing about them collected over years. But you want to train a neural network. You want to ask, essentially, a neural network, tell me the salient things about this population. What is interesting? Here's a bunch of stuff we collected. We don't have time to sift through. We don't have the attention span. We don't have the memory to sift through every single point and compare and contrast all this other stuff. So you ask the neural network, give me the highlights. Tell me what's meaningful in this data. What do these data mean? And using feature extraction, dimensionality reduction, which can then lead to clustering as a next step, the neural network will learn what is important. Maybe it learns migration patterns versus just milling around. Maybe it looks at the GPS data and it learns overall patterns versus the monkey climbed this tree instead of this tree today. That sort of thing. And the neural network can be trained on a huge data set that no human could ever manage. No team of humans could ever manage. Get it down to a manageable size where the human can start looking and going, oh, that's interesting, and then look further into it. And then find features, such as if it finds migration patterns, it finds features in the GPS data, and then the human uses a different unsupervised learning algorithm to learn more about the migration, which can even inform next year's research. Maybe they changed their methodology to get better data. They see something interesting they want to explore. That's unsupervised learning. Finding the order in chaos, looking at the cloud and seeing, oh, that looks like a unicorn. It looks like this piece of toast has Jesus Christ's face on it. Whatever. Finding order in the universe. Semi-supervised learning is just, you have some labeled data. So supervised learning, the data are completely labeled. Unsupervised learning, it's just a mess of data with no labels. And semi-supervised is half and half, or part and part. That's all. It just means you've got some labels, and maybe those labels are enough. You want to learn more labels. You get the idea. But then we get to my favorite, which is reinforcement learning. This is the true human learning method. Reinforcement learning is what's called a bootstrapping method. Basically, remember my little story about the human baby? Or any baby? That when it's first born, it has certain instincts, it has certain things that are hardwired, but mostly it just flails around and doesn't know how to do anything. But as it flails around, it gets better and better and better at flailing until it's flailing with a purpose, and then we don't call it flailing anymore. Reinforcement learning is where you see Boston Dynamics. If you go on YouTube and see them, it's really cool. Go look up their videos. So you've got the little Boston Dynamics dog. And at the beginning, the dog just falls over like an idiot. Bam, 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 it's rolling all over the place. And then it gets better and better and better at walking, and now it's doing little dances and grooving to a beat. They use reinforcement learning and probably more advanced techniques, but at its core, reinforcement learning that basically says, moment to moment, are you falling down? If so, that's bad. If not, that's good. Something called temporal-difference learning is the most common form of reinforcement learning. Temporal-difference learning is basically working in time steps, moment to second, however you define it. Maybe you're playing chess and it would be turn by turn. Each turn would be a time step. Reinforcement learning, there's a value function. Basically, you have a score, like a video game score. A higher number might be better, a lower number might be worse. And over time, you want to get the best long-term score possible, like money. Let's say you could do this thing and make this much money and do this thing and make this much money. You're going to pick the thing that gives you more money. But let's say, a year down the road, maybe you'll ultimately make more money doing the other thing, even though you don't get the money right now, like investing. Maybe you'll have less money second to second, but eventually you'll have more money. That's kind of how reinforcement learning works. It has a score function. You define the value. You tell the neural network if it's doing well or not. It's like training a dog. If the dog pees on the carpet and you don't want it to, you tell it it's bad. If you want the dog to sit down and stay, and it does, you tell it it's good. That's how reinforcement learning works. It has a numerical score which tells it whether it's doing poorly or well, and the algorithm follows the higher long-term score. Temporal difference learning is a method of figuring out what this value function is. Reinforcement learning is just, you have a value function that says whether something is good or bad, long term, and you somehow update that value function during training, and then after training is done, it just follows the value function, and that's how it makes decisions. It picks the high value option. Temporal difference learning is one way of figuring out what that value function is. And the benefit of it is it requires no knowledge whatsoever. In fact, when you start training something by temporal difference, your neural network, all the math in there, you just set it to random values. You could set it all to 0. You could set it using a Gaussian distribution. You can just roll a die, pick random numbers, pick the temperature of your CPU from moment to moment, whatever. The initial value of the neural network is meaningless. And so it has a value function, and the value function is completely random and wrong. So what happens is, in temporal difference learning, the neural network chooses an action based on the value function it has. And then you tell it whether it did good or bad. If it did good, then it makes a note in its own numbers and says, the thing I just did increased the value. So if it was 3, now it might be 3.1. It'll say, okay, I got a reward. In the future, I'm going to do that more. Or if it was bad, it might put it back down to 2.9 and say, okay, that didn't work out great. I'm going to put it back down and say, I'm going to do that less in the future because I was scolded. So as each time step goes by, you're giving feedback to the neural network to tell it, you did good, you did bad. And the neural network is tweaking its own values to do things that it was rewarded for more and it was scolded for less. But only a little bit because, again, it wants to be long-term reward. Maybe, you're playing chess and you move your pawn and your pawn got taken. You lost a piece. That's bad. So it's going to devalue the move it just made and say, oh, well, that was a bad move. But what if that caused the opponent to, as a result of taking that piece, the opponent made a move that made them vulnerable, and now you can sneak your bishop in, and all of a sudden they're in check. So long term, that was actually a good move because you tricked your opponent. It was a sacrificial piece or whatever. So in that case, maybe you don't tell the network that losing a piece is bad. Maybe you don't tell it anything at all. Maybe turn to turn to turn, you just leave it alone, and it'll do all its moves, and then at the end, it'll win or lose. If the neural network wins, then you give it a big reward. And if the neural network loses, you give it a big scolding. And then it goes back and it takes the path of moves it made. It looks at all the moves it made that led to a good or bad result, and it tweaks them to say, okay, I won the game, so all the things I did make them a little more likely. Which doesn't mean it would ever make those same moves again, because the opponent could make different moves. But if it finds itself in that sequence of moves or something similar, it might try to go for it and see if it can get the same thing to happen again. And maybe it wins again by a slightly different set of moves, and so everything's reinforced to say, okay, now we're talking about, you might have heard of things like openings and gambits, how humans analyze chess games, certain sets of moves that set up the board a certain way. Maybe the neural network kind of learns those to say, well, early castling is valuable, or moving the pawns on this side of the board when this is going on is valuable. And these kinds of things just get incorporated into the neural network over time. You've heard of AI, modern AI. In the past, the computer programs that would try and play chess were manually programmed. People took all of those documentations, the openings and gambits, and all the things somebody trying to learn chess will read about, and incorporated them into a computer program and made a pretty good one. But there was a very smart person, I forget their name, but they decided to try something different. There's a game called Backgammon. It's another board game. But basically, they decided, I'm not going to try to write one like that. I'm just going to use temporal difference learning. My training program knows the rules of backgammon. It knows what moves are legal, and it knows whether you win or lose, but it doesn't know any strategy or anything, all right? So the neural network at the beginning is making random moves and doing stupid things, and it'll probably lose every time to a human. But the trick is you have the neural network play against itself. The same untrained neural network plays itself, and it's making random moves, nonsense moves, against itself. But eventually it'll win or lose. And when it does win or lose, you take the win condition and you tweak the network based on that. You take the lose condition, you tweak the network based on that. And it actually gets a tiny bit smarter from initial randomness. And you do it again and again and again and again. And this is how people are making AI that win at chess that win at Go, the unconquerable game. To actually make an AI, a computer program that can beat humans at Go, was astonishing. I remember reading about the one person who, one of the best Go players in all of the world, of this unconquerable game that no computer could ever play as good as a human. And then the computer won, and this person was just set on fire and went after the AI and was like, I need to learn what you did. I need to understand what you did. And this person is learning from the AI and getting better at Go. It's how people made robots that play League of Legends, all this other stuff. It's how a company called DeepMind created a neural network, an AI, that could play a whole bunch of old Atari games with no pre-training whatsoever, with no human intervention whatsoever, other than setting up the training and leaving it go. To the point where their program got so impressive that Google just decided to buy them. And now they're part of Google. And go look up DeepMind. Some fascinating things have come out from them. So that's reinforcement learning, is just, instead of having a task, right, you don't have something that you're trying to learn. You're not trying to find the order in chaos. You're not trying to perform a predetermined task. You are given a score, and you want to maximize that score, however the human decides what that score is. If you're playing a video game, the score would be higher for winning. If you're making a dog robot, the score would be higher for not falling over. And over time, the robot learns how to not fall over, because it gets a reward the longer it walks without falling, and every time it falls, it gets a huge scolding. So the robot learns what it did in terms of moving its limbs to make it not fall, and eventually it doesn't fall anymore, because it's following the higher value it has learned. And I mentioned something called meta-learning. This is just using neural networks to learn about training neural networks. Because, again, we don't really understand everything about neural networks. They're kind of a black box in many ways. It's an active field of study. Why does this work? It's kind of like quantum mechanics. We know the math of quantum mechanics. It works. Quantum mechanical computers are real. We know about tunneling. We know about entanglement. We know about all these things. We know the math. But why? It's really weird. There's an entire Wikipedia page about all the different hypotheses, or even just ideas, people have about why quantum mechanics make sense. But we have the math. It works. It's not arguable. It's just like neural networks. You train a neural network, it'll win at chess. But we're trying to figure out why. So they use neural networks. Unsupervised learning, I suppose, is one of the techniques to say, here's a whole bunch of neural networks we trained. Here's how well they perform. Here's how they performed during their training, how they got better and better and better. They throw a bunch of data at the wall, and then they use a neural network to figure out patterns in that data, in those data. That's all meta-learning is. It's not really a different kind of learning. It's just an application of it. So supervised learning is you have a task, you want the neural network to do it. Unsupervised learning is you have data, and you want the neural network to figure out things about that data, seed order from the chaos. And reinforcement learning is basically human-style learning, or intelligent life form style learning. You just go through life and you have a goal. You don't have a task, you have something that tells you whether you're doing well or not, and you just want to do well. So this was a long, rambling video, and I wonder how many people are actually going to watch to this point. If you did, you must just like the beard. So my thanks for sticking it out. So there will be plenty of AI videos in the future, plenty of electronics videos. I've got a bunch of math videos coming up, and all of this is related. If you thought this was just an electronics channel, well, there is still an electronics focus. Like I said, AI can be used for training robots. One idea I have is making an AI, making a neural network that will play chess, but incorporating it into a real electronic chessboard. So instead of playing on your computer, you play on a chessboard and maybe little lights light up to tell you what the computer wants to move, or something like that. I think that'll be a cool idea. So all kinds of good, fun stuff coming in the future. For now, I'll be seeing you.